Hello, everybody. This is Professor Ma, and this is the sections on the fundamental theorem of algebra. Uh, the fundamental theorem of algebra basically, we're going to do in two parts. The first part basically says the complex numbers is complete. So here's the statements. We have a polynomial degree n, then it has exactly n complex roots, up to including the orders, of course. And so this is the completeness of the complex numbers. Okay. This is particularly important of importance because after before this, and one of the question is, where do numbers stop in terms of solving polynomial equations? And then this answer the questions basically says, well, you don't have to worry anymore that you don't have enough numbers because complex numbers is it for solving polynomial equations. Okay. And the second part concerns the real polynomial. That real polynomial means the coefficients are real numbers. We don't use, so we don't have things like x plus 1 plus I times x squares. We don't allow to use in complex coefficients. So real polynomials or real number polynomials. Okay, and then if a root, complex root, a plus bi is a root, then its conjugates, it must also be a root. So then from there, we can actually write down what does how does a real polynomial factor into the form that it will factor into completely. So the first part, completeness theorem, is in part, we cannot do the proof in this course. But the second part, we can verify. And the point about verifying the second part is that the following. That is, if we let z and z star be conjugate pairs, okay? So this is conjugate pairs. So if z is 3 minus 2i, then z star 3 is 3 plus 2i. So with the signs in the middle difference. So the basic things that we want to prove over here for polynomials is that if we plug in the conjugates of a complex number, this turns out to be the same as just plugging the original. After you get the answer, then conjugates the answer of the conjugates. Okay, and so this basically we go through these verifications. It's very easy to check, multiply out. So to see the second part, you just multiply things out. Okay. And you can pull the constant out of conjugations. And from these, and the same thing, if you raise to nth powers of conjugates, it's the same as raise the power to nth power first. That take the conjugates of that answers. Okay, and so then we wind up with the proof by step, and using all the property we just went through. Then plugging in the conjugates is the same as plugging in the original, then conjugates the answers. And what does that mean? It means that if I were to plug in this equal to 0, if z is conjugate is a root, then this gotta be 0. Okay, it goes both ways. So if I plug in p of z is 0, a complex number is 0 as a root, then its conjugates must also be 0, is a root, vice versa. Okay, so that's the second part of the about the the real roots and the complex roots of a real polynomial. So here's some examples. So what kind of exercise can we, do? What the exercise, so we can actually construct the polynomial if I give you a complex root. And here's what we do. Okay. Notice if I get a conjugate pairs, if I add them, okay, notice I will get twice of the number 8. If I multiply them, I get a squared plus b squared. Okay, and from here, notice that if I have two conjugate roots, z and z prime are conjugates, and if I multiply them expanded, then this 2a goes in as a coefficients in front of the x, and a squared plus b squared is the constant term. So, so what? So this gives us a concrete way of constructing second degree polynomial. Here's an example. Okay, suppose I have a second degree polynomial. Find a second degree polynomial with this as a root. I don't even have to tell you this one. Right? If I tell you, say, oh, 3 plus 2i is a root, then you can infer immediately its cousin, 3 minus 2i is all its conjugates. It must also be a root. Okay. So in this problem, it tells you, okay, well, it tells you both are roots. And find a polynomial that have these two complex numbers are roots. Meaning, find a polynomial when you plug in the quadratic formulas, it simplifies into these two numbers. Okay, and it's very easy. And the way you do it, you add them, get 2a first, okay, and multiply them, and that's a squared plus b squared. 9 plus 4 is 13, and then you just put the 6 minus 6 right there, and plus the 13 at the end, and voila, and that is the second degree polynomial. Oh, by the way, x squared minus the 2a times x plus the product. It's just a plugging in procedure, okay? Just a trick. And why? Because it's on the homework. So it's nice to know that you can just do this really fast and produce a second degree polynomial with a specified roots. And so now, on the other hand, there are many polynomials with the roots z and z prime. I can multiply these polynomial by any constant. In other words, in the answer over here, I could have any constant times this polynomial. They have the same two roots. Now, so if I want to nail down a particular one, then we, of course, is give the initial conditions, and the problem will be phrased in these manners. It will tell you, says, for instance, that when you put in x equal to 1, the polynomial will calculate the output is 2. Okay. So from the previous part, I know the polynomial q must be some constant times the polynomial, the answer we got. On the other hand, when I put 1 into this polynomial, I suppose to get 2. Okay, this output is supposed to be 2 when 1 is put into the x. And that leaves the k into becomes equations. Okay, so in other words, I have ak equal to 2. Here's the equations. Okay, so this should be supposed the output is equal to 2. So I got ak is 2, so k is 1/4. And therefore, the q must be this a quarter times this formula. And so this is we call a specific answers with these initial conditions. Okay. So Here's then from the roots of real polynomials that has to have if it's a real root, then if r is a real number root like x 2, then x minus 2 has to be a factor. Or else, if it's not real root, then it comes in pairs. It comes in z and z conjugates. It comes in the second degree polynomial, like one of those we just made up. So therefore, this is how real coefficient polynomials will factored into. Okay, so that's why it's called a factorization theorem. Therefore, any real polynomial must factor into the following format. Okay, if the number, coefficient if in the front is a, let's take the number a out of the picture. So I start out with xn, and so on. So I'm factoring this part, starting out with inside the parentheses, starting out coefficient 1, of course. In other words, I'm going to have a bunch of x, and x in the front. Okay, so and the a in the front. Okay. And then it breaks up into the following factors. We're talking about how these factors. It factors into a bunch of linear ones, x minus and numbers, and those are the roots. Each number is a real number, is a root. And then you have a bunch of second degree polynomials that have no real roots. They give complex root and they give conjugate pairs of complex roots. Okay, so any real polynomials factor into this format, first and second degree. Okay. So we don't need third degree. There's no tag allowance third degree component that's needed. And this is very important. That basically breaks every real number polynomial problems into first degree and second degree problems. Okay, that's why first and second degree are so important. And so here is an example that's doable. Of course, in general, this is extremely difficult to do. Okay, so here it breaks into the third degree polynomials, and so then the two quadratics, there's no real roots. We put in the quadratic formulas, now we get two sets of complex roots. Okay. So this is complete list of the roots, and then the factoring into real numbers, okay, without using complex numbers. Factoring completely in real numbers. Then what kind of problems we will have? Well, in the homework, one type of problems is that we make up the polynomials with the specified roots. Okay, here is degree 5 with root 1, I2, also degree 5. Sorry, with 1, I is a root, minus I has to be a root. 2 minus I is a root, 2 plus I has to be a root. Okay, so those are inferred because they are conjugates. Okay, so hence the complete list of root is 1, I minus I, 2 minus I, 2 plus I. Okay. X minus x1 has a root, therefore a factor must has a factor x minus 1. I minus I, then remember we use that way to construct the polynomial for that. And excuse me, that will be x squared plus 1. Okay, remember add these two numbers is 4, 2a is 4. A squared plus b squared is 5. So for this is a second degree polynomial, x squared minus 4x plus 5. Excuse me. So that's what p of x must be up to a constant multiple. Then we plug in 0. with the initial conditions, and then we find out what k is. That's it. That gives you the specific polynomial, okay, with these rules and initial conditions. Okay, that's it. Bye-bye. Do the homework.